Welcome to Real Physics, another stunning conversation with ChatGPT about fundamental physics with the new model O3, how to make progress, real progress, and possibly find a way to a theory of everything. It's really interesting. If you haven't seen the first part, you might watch it, but you don't have to. Let's go right into the discussion here. I would like to continue our discussion about fundamental physics based on the premise that progress is measured by the elimination of constants of nature. I would like to discuss that concretely. We should first agree on a reasonable set of these constants of nature, or free parameters if you want, which possibly could be explained in a best case scenario. Which constants come to your mind? I show you a little bit the thinking, it's a long thinking process anyway, but let's listen to his answer now.
A natural starting point is to focus on the dimensionless numbers that remain once we've adopted natural units. For example, one can list the fine structure constant, AFU 137.
Agree.
This governs the strength of electromagnetic interactions. 2. The proton-electron mass ratio, 8836.
Good point.
A key number in atomic physics whose origin remains unexplained. 3. The strong interaction scale, often expressed either by the strong coupling constant at a reference energy or as LQCD in Planck units. 4. Electroweak parameters, for instance, the electroweak mixing angle, or equivalently the ratio of the W and Z boson masses that quantifies the unification of electromagnetic and weak forces. 5. The Yukawa couplings of fermions, a set of about a dozen numbers if one counts quarks and charged leptons, and more when neutrino masses and mixings are included, determine the masses of elementary particles. 6. CP violating phases, such as the phase in the CKM matrix, which has deep implications for matter-antimatter asymmetry. 7. The cosmological constant, when expressed in dimensionless form relative to the Planck scale, it poses one of the greatest puzzles in modern physics. Overall, the standard model is often said to contain roughly 19 free parameters, or more when neutrino properties are included. And when cosmological parameters are added, the tally can rise to 20 to 30.
Ridiculous.
In an ideal TOE, these numbers would not be arbitrary inputs, but would emerge from deeper mathematical or logical principles.
That's what I say. Fully agree with 1 and 2. Then you list the parameters of the standard model, of which I'm very skeptical. Maybe I have been sometimes too polemic in my writings, but let's say just this. To anyone who wants to compute all these numbers, I wish you good luck with that. For that reason, I propose to focus on the era before 1930. If we can resolve some of the fundamental issues back then, the standard model probably would become obsolete. Can you thus propose a set of constants of nature which were known around 1930? Again, reasoning process. You can watch this, then I close it.
Certainly. Focusing on the period before 1930, one might list these as the key constants. 1. The speed of light, c, central to electromagnetism and the newly emerging relativity. 2. Newton's gravitational constant, g, governing gravitational interactions. 3. Planck's constant, h, introduced with the birth of quantum theory. 4. The elementary charge, E, fundamental to the emerging picture of atomic structure. 5. The masses of elementary particles, primarily the electron mass and the proton mass in them, whose ratio forms a key dimensionless number. In this era, these constants, when combined into dimensionless numbers like the fine structure constant, I equals E forward 4 pi Chirac C, and the proton mass ratio, represented the mysterious numbers that later revolutions aim to explain.
Okay, for not missing the big picture, I would add the mass and size of the universe, and also the size of the proton, even if this is a more recent measurement. The electrical constants can be absorbed into the fine structure constant, 1 over 137 roughly. You're correct. Thus, I would propose the following list of 9 constants: 137, 1836, C, H, big G, the mass and size of the proton, the mass and size of the universe. Do you see anything inconsistent, incomplete, or redundant here? Please be as critical as possible. Now, we want to include cosmology here, and talking about cosmology, there is an upcoming conference you might wish to participate in where you can discuss with me and other experts the crisis in cosmology and explore alternative ways. It's organized by Anastasia and Shiloh, who have a wonderful podcast, the Demystifying Science podcast. I have been there several times, and yeah, would be great to see you and discuss with you cosmology in person in Portugal. Get your tickets now. See the link in the description. Now we go to the answer of ChatGPT. I'll let you show the reasoning. Okay, there's a lot of thinking here. Okay, zack.
Your list is an interesting starting point, but there are a few points worth scrutinizing. 1. Mix of dimensionless and dimensionful numbers. The fine structure constant, 137, and the proton-electron mass ratio, Watthen 836, are dimensionless and thus are independent of our unit choices. In contrast, CHG, MPAR, RHI, ME have values that depend on our chosen units. A truly fundamental list ideally emphasizes numbers that remain invariant under unit changes.
Kind of disagree.
2. Redundancy between m dHack and the mass ratio, including the proton mass m tri, along with the ratio m/m 1836, implicitly defines the electron mass. If the electron mass is not listed separately, one might question whether MA is fundamental or simply serving to set a scale. One could argue that only one of these masses is truly independent.
That's obvious.
3.
Yeah.
The status of the proton size. The size of the proton is an emergent quantity determined by QCD dynamics. Although it is an important scale, it is not fundamental in the same sense as C, H, or G,
I would
but
argue
rather a
it is.
consequence of the strong interaction. In a pre-1930 context where QCD was unknown, one might argue over its status as a constant of nature. 4. The universe's mass, m's, and size are. These quantities are highly model dependent and subject
Fair
to change
enough.
as our understanding of cosmology improves.
Okay.
They are often regarded as boundary conditions or large-scale parameters rather than truly fundamental constants. In modern discussions, the cosmological constant Lil, or its dimensionless version, might be seen as a more intrinsic quantity.
Yeah, it's a patch.
Completeness versus practicality. Your list aims to capture both microphysical, 37-1036, CHG, Emish, Arsha, and cosmological, R scales. While this is useful for a big picture discussion, it may mix two different kinds of constants, those that appear in our fundamental laws and those that arise from initial or boundary conditions.
The same stuff.
A minimal set of truly fundamental constants might be smaller if we choose a natural unit system, e.g. Planck units, and focus on pure numbers.
Kind of disagree.
In summary, your list is a plausible and provocative choice, but it is not unique. One might argue that it mixes parameters of different origins and levels of fundamentality. A more refined list might favor only dimensionless numbers or replace Empson and R ray with something like the cosmological constant, thereby keeping the focus on constants that are intrinsic to the laws of physics rather than emergent large-scale properties.
I could have mentioned here Dirac's large numbers with which you can transform, say, the mass of the universe to the mass of the proton. But anyway, we come back to that discussion. Thanks for your critique. First, we have already discussed that dimensional constants such as big G are also messages of nature to be explained. Absolutely. No discussion here. Second, in contrast to the proton, the electron has no measurable size. That's why we're considering the size of the proton only. Third, the size of the proton is not an invention of quantum field theory, but is known as a matter of principle since the scattering experiments of Rutherford in 1914. Fourth, it is true that the cosmological quantities are model dependent. Nonetheless, they exist and we can talk about orders of magnitude. Fifth, I would not distinguish between constants and boundary conditions. It would be unsatisfactory not to explain the latter. So I would like to proceed with this list of 9 if you don't mind. I guess you can agree it's a fairly reasonable choice, or at least revolutionary progress if we eliminate one of them, right?
I agree that, given our premises, this list is a coherent and provocative starting point. If we can explain or derive any one of these 9 numbers from the others, or from a deeper theory, it would indeed signify revolutionary progress. Let's use this set as our benchmark for further discussion.
Evidently, the two numbers can be computed as a matter of principle. Feynman once said that every good theoretical physicist put this number 137 up on his wall and worries about. And Dirac pondered for decades of how to compute the mass ratio of the proton and electron, 1836. Thus, if a true genius comes along, he might come up with a theory producing these two numbers, right?
Yes, that's the hope. In principle, if we had a truly fundamental theory, a genuine theory of everything, it should yield those dimensionless numbers from its internal logic rather than leaving them as arbitrary inputs. In practice, however, past attempts, such as Eddington's or Dirac's proposals, have struggled to produce convincing, widely accepted derivations, and many results have bordered on numerology. Nonetheless, deriving 137 and 1836 from first principles remains a powerful guiding goal for fundamental physics.
Well, Eddington was probably mocked for good reason, but I think there is a deep truth hidden in Dirac's large number hypothesis. Do you understand how it relates to the 9 constant I mentioned above? Yeah, it's strange here because the reasoning all of a sudden starts to be in German. So I don't think it's interesting for you if I show you that. I put the link of the entire discussion in the description so you can follow up and let it translate if you like.
Yes, Dirac's large number hypothesis is essentially about noticing that certain huge dimensionless numbers, formed by combining microphysical constants with cosmological scales, turn out to be of comparable orders of magnitude. For example, if you take the ratio of the electromagnetic to the gravitational force between a proton and an electron, you get a number on the order of 1039 to 10⁻40.
Right.
Similarly, if you form the ratio of the size of the universe, Ri, to the size of the proton, Ri,
right,
or compare the mass of the universe to the proton mass, Mi, you obtain
yet another number,
enormous numbers. In your list of 9 constants, the first two, 137, the inverse fine structure constant, and 1836, the proton-electron mass ratio, are dimensionless numbers that appear directly in atomic physics. The remaining constants, C, G, Mt, Rt, Mri, can be combined to form other dimensionless quantities. Dirac's insight was that these seemingly disparate scales, from atomic to cosmic, might not be independent but related by deep principles. Thus, if a TOE were to explain these 9 constants, it would likely also account for why these large ratios come out so similar. In other words, Dirac's hypothesis suggests that the microphysical constants, like 137 and 1836, along with C, H, G, M, Ra, and the cosmological constants, Mf and Ra, are intertwined, and their large number coincidences are clues to an underlying unity in physics.
One should add that the large number involving the masses, 10 to the 80, is the square of the other two numbers, 10 to the 40, which makes it even more unlikely that this is just a coincidence. Given that Dirac's hypothesis consists of 2 independent equations, would you agree that if all this is backed by a sound theoretical framework, it would eliminate 2 constants from our list?
Yes, I agree. If Dirac's large number hypotheses are underpinned by a sound theory and can be expressed as 2 independent equations, then 2 of the constants in your list would no longer be free parameters. They would be derivable from the others. This would effectively reduce the number of unexplained constants by 2, marking a significant unification and simplification in our understanding.
Well, I guess this should be a motivation for researchers to ponder over Dirac's ideas. If we assume 137 and 1836 are already computed, then our list has shrunk to 5 numbers now. Do you have an idea how to get rid of another constant based on a similar coincidence involving the above constants? Now he comes up with something very interesting. Really crazy, thinking for 33 seconds.
One idea is to look at the proton's size in relation to its quantum mechanical scale. For example, notice that the measured proton radius Rp is of the same order as its Compton wavelength.
Very
Lambda
interesting.
p equal h bar mpc. If one could show from a fundamental theory that the proton's spatial extent must be proportional with a calculable coefficient of order unity to its Compton wavelength, then Rp would no longer be an independent parameter. It would be determined by H, MP, and C. Another possibility is to exploit relations in the cosmological sector. Dirac's large number coincidences hint that the cosmological MEMU and radius RU are not independent but satisfy a relation like frac MU MP, sim left RU RP right 2.
Yeah.
If this relation is elevated from an observed numerical accident to a principle derived from a deeper theory, perhaps emerging from a synthesis of quantum mechanics and gravitation, then one of the cosmological parameters would be calculable in terms of the others. Either approach would eliminate one constant from our list by showing that what we thought was free is in fact determined by other constants. So yes, if a sound theory could justify one of these relations as necessary, that would indeed remove an independent constant from our set.
Well, I really love that he brought up this Compton wavelength issue. That's fantastic. My answer, I guess we have already taken into account your last point, a possible explanation of Dirac's observation, which brought our list down to 5 constants. However, I'm really stunned that you mentioned the coincidence of the Compton wavelength of the proton. Then I mentioned that I have shown in another video, and I cannot go into the details right here, but I urge you to watch this video where I explain in detail that the Compton wavelength of the proton, being of the same size of the proton radius, is indeed equivalent to one of Dirac's observations, but it needs a little bit of calculation, and yeah, here's the video. So I just told him here, I have shown that this is equivalent to Dirac. And then my question, however, do you see yet another coincidence involving big G? Yeah, and I thought he would come up with a simple thing now, and really something very strange happened here.
One possibility is to consider what's sometimes called the Eddington-Weinberg relation. In that coincidence, one forms the dimensionless combination for h bar to hg mp3, where h is the Hubble constant. Amazingly, with the measured values, this ratio comes out to be of order unity. This suggests that the gravitational constant G isn't an isolated number, but is tied via quantum bar and relativistic C parameters and the proton mass MP to the cosmic scale through H. If a deep theory could explain why this combination must equal 1, then G, or equivalently H, if the others are known, would no longer be an independent free parameter. This would eliminate another constant from our list in much the same spirit as the Dirac large number coincidences.
Wow, you thought for a long time, 48 seconds, congrats. I guess it was von Weizsäcker, however, who first noted this particular coincidence. And again, it is yet another form of Dirac's observation, which is not always easy to see. And I think I have to break down that a little bit, so I made up a little file here to show you better why this is indeed equivalent, what he mentions, but it's very interesting. So here we are. We start with the formula he proposed here. And, well, I put h bar is h over 2 pi, so we get this. This is the, you see that the equivalence of the formula. Then, of course, the Hubble constant, C, is just a measure of the age of the universe. C over the Hubble constant is what you might call the radius of the universe. Of course, we're talking of orders of magnitude here. And then you can transform that to, you put the radius of the universe here instead of h over c, and then you split up this m of the proton to the 3rd power. You split that up, one mass is over here, and instead of mp, I write m electron times 1836. And now you notice here in the denominator you have big G, the product of electron and proton mass. That reminds you from the gravitational force in a hydrogen atom. And the electric force in a hydrogen atom is instead, well, it's E squared over 4 pi epsilon naught. And this is the electric force is of the same order of magnitude of hc. If you consider that hc is nothing else but, well, the electric constants expressed by the fine structure constant. So in short, if you cancel out the inverse square law, in short, the blue numbers you have here is the electric force divided by the gravitational force, which is of course Dirac's large number. I highlighted here the radius of the universe, and the radius of the universe, you may write it as 10 to the 41 as the radius of the proton, and then you have the ratio of Dirac's large numbers here, 10 to the 41, cancelling. And then you end up with, well, a numerical factor. Indeed, this is not unity. This is 10 to the minus 4th, his expression. And then you end up with h over rp, which a over rp cmp. And this is, of course, order of unity because we have this other coincidence I explained before, which is again equivalent to Dirac's large numbers. So yeah, it's not always easy to see, but we have this a lot of nice coincidences with at the very end boil down to Dirac's observations, but you have to have a little bit experience to see that. I continue. If you assume another coincidence I had in mind, which is much simpler, so technically you already discovered it. The simple form, however, is g, gravitational constant, is speed of light squared times the radius of the universe divided by the mass of the universe. Are you aware of that?
Yes, I'm aware of that relation. G equals frac C2RU mu. It expresses the gravitational constant in terms of cosmic scale parameters, the universe's radius and mass, and the speed of light. This relation is often discussed in the context of Dirac's large number hypothesis and resonates with Machian ideas, suggesting that what we view as a fundamental constant might instead be derived from the overall structure of the universe. Although the precise definitions of RU and MU can be model dependent, this simple coincidence fits neatly into the broader strategy of reducing free parameters by showing that constants like G may emerge from deeper cosmic boundary conditions.
By the way, very interesting. It's in German, but he mentioned here, I think, even Sharma and another paper I'm going to read, but he mentions Sharma. I always talk about Sharma and Dicke, and well, he is aware of that. Yeah, simply stunning. Okay, assuming again that we have a neatly developed theoretical framework that justifies this coincidence, we would be down at 4 fundamental constants, having explained big G. I should mention that the list implicitly contains the age of the universe, which appears hard to justify from first principles. That means we could be down to 3 constants left to explain. Do you agree?
Yes, I agree. If our theoretical framework can derive both 37 and 1836 and further relate G to the cosmic parameters via G equals C quit RU or MU, then from our original 9 constants, we'd effectively eliminate 2 independent parameters, leaving us with 4. Since the age of the universe, or equivalently, its mass and size, is notoriously difficult to derive from first principles and might be treated as a boundary condition rather than a truly fundamental constant, we'd effectively be left with 3 constants that need a fundamental explanation. This dramatic reduction aligns with the goal of a TOE to explain as many free parameters as possible from deeper principles.
Well, I should have mentioned that, of course, the mass and size of the universe, it's an observational problem to determine it very precisely, but as a matter of principle, it can be a very well-determined number, so no problem about that. Little correction, I still don't like the boundary conditions. I just assume they could be properly explained by a theory that justifies Dirac's large numbers, eliminating another 2 constants. The next step is a tricky one. It involves considering physical units such as meters, seconds, and kilograms, one of which we should also get rid of.
Indeed, that's a key point. In a fully fundamental theory, the system of units, meters, seconds, and kilograms, should ideally emerge from the theory rather than be imposed arbitrarily. In many natural unit schemes, for example, by setting CAG equal to 1, the mass scale becomes fixed in terms of length and time, or vice versa, so that one of these units, typically the kilogram or the mass unit, is no longer independent.
No,
if the theory can explain why particle masses appear as specific dimensionless fractions of a fundamental mass scale, say the Planck mass, then the kilogram is no longer free but derivable. This is analogous to eliminating free parameters via numerical coincidences. So yes, eliminating one of the base units would further reduce the arbitrariness in our constants, and that would be a major step toward a true theory of everything.
A few caveats here. First, beware of superficially sweeping the problem under the rug with natural units. This has no explanatory power. Second, in the spirit of Dirac, Planck's units are nothing fundamental. The fact that they differ by 20 orders of magnitude from the nuclear scale just comes from the fact that the square root of Dirac's 10 to the 40 is taken. However, it is true that the 3 constants C, H, and G generate the units meters, second, and kilograms. Since we have eliminated G, we should therefore strive also to eliminate the unit kilogram. Are you following me?
I follow your reasoning. Simply adopting natural units doesn't explain why the numbers have the values they do, and Dirac's viewpoint tells us that the Planck units aren't intrinsically fundamental. Since C, H, and G generate the standard units, meters, seconds, and kilograms, and we've now derived G from cosmic parameters, thereby eliminating it as a free parameter, we should indeed strive to derive the mass scale, That is, to eliminate the kilogram as an independent unit. In other words, a truly fundamental theory should express particle masses, and by extension the kilogram, in terms of CH and the remaining dimensionless numbers, like 137 and 1836, rather than treating them as arbitrary inputs. This would be a significant step towards showing that all units and constants emerge from deeper principles rather than being imposed externally.
The idea, it goes back to Julian Barbour, The End of Time, it is to express mass by inverse accelerations, thus automatically implementing Newton's third law. If one had, for instance, a microscopic theory of the proton, then you could relate its mass to some internal acceleration, say c² over the radius of the proton. Putting in the numbers, 1 kilogram would then be a numerical factor times second squared over meters, an inverse acceleration, thereby eliminating another constant.
Indeed, that's a promising approach. As Julian Barbour and others have suggested, if one can express mass in terms of an inverse acceleration, essentially relating it to the dynamics of the system, then mass loses its status as an independent unit. For example, if a microscopic theory of the proton shows that its mass mp is determined by an internal acceleration scale of order c2 or rp, then we could express mp, and hence the kilogram, as a numerical factor times s² of m. In such a framework, the unit of mass would be derivable from the units of length and time, along with fundamental constants like c and h, rather than being arbitrary. This step would further reduce the number of free parameters, moving us closer to a theory where all constants emerge from deeper principles.
If you don't mind a little test, if you have followed me, if you substitute the unit kilogram as above, what physical unit then Planck's constant would have? And now he really stunned me. That's amazing. In a few seconds, yeah, I don't let that read because it's a little annoying how he reads the formulas, but he understands it. I mean, if you put in an inverse acceleration instead of kilograms, the unit of Planck's constant is just meters times second. Wow. Really great answer. Congrats, that was very fast. A good point to interrupt and continue another time, since we really hit a wall here. C and H cannot be explained as before. Even if you assume incredible smart theories, there is simply no coincidence that could eliminate C and H together with their units, meters and seconds. Do you agree, or am I mistaken?
I agree. Despite many clever approaches, C and H seem to play a unique role as the very conversion factors linking space with time and energy with frequency. They define the underlying structure of relativity and quantum mechanics, respectively, and no known numerical coincidence or symmetry appears capable of eliminating them from our list. In other words, while many other constants might be derivable from deeper principles, C and H remain foundational and irreducible in our current understanding.
Yeah, I hope you enjoyed this discussion. If you want to go still into more detail, you can have a look in my book. It's basically the second part of my book, The Mathematical Reality, where I discuss in even more detail all the arising problems and how to possibly eliminate one constant after another before we hit the wall of not being able to explain H and C. This will be our last session then. And well, if you enjoyed the video, don't forget to like it. And if you're interested in fundamental physics, you should definitely subscribe to this channel.